Okay, so in this video, we're going to talk about how you would compare the relative strengths of intermolecular forces, as well as talk about some of the different properties that can be affected by intermolecular forces, such as viscosity, boiling and melting point, vapor pressure, and surface tension. All right, so when we come to comparing these three intermolecular forces, so remember we had dispersion, which every molecule is going to have dispersion because every molecule has an electron cloud that can be polarized to some extent. Dipole-dipole force, which is two polar molecules attracting each other. And then hydrogen bonding, which is molecules that have an NH, OH, or FH bond, creating a really strong dipole that can attract to other molecules. The general comparison is that on an individual molecular basis, hydrogen bonding is by far the strongest of the three forces, followed by dipole-dipole, and then dispersion is the weakest of the three. Like I said, that's on a molecule-to-molecule basis. Once you get really, really heavy, large molecules, though, things that have very large electron clouds that can be really polarized, dispersion can potentially overtake the strength of other forces. So again, what you're looking for is compare molar mass generally. If the molar masses are about the same, hydrogen bonding is the strongest. If the molar masses are absurdly different, and you'll be able to tell because they'll make it really obvious, then you go with the heaviest molecule because it has the strongest dispersion force. One other thing to keep in mind is that dispersion forces only take place in what we call condensed phases, which are aqueous solutions, liquids, and solids. You will not see intermolecular forces in an ideal gas because one of the properties of an ideal gas is that the particles are so far apart, they have no attractive forces whatsoever. Now, one of the things we're going to talk about later in this unit is the difference between an ideal gas where intermolecular forces don't exist and a real gas where intermolecular forces do kind of exist. All right, so I should also at this point go over a fourth force. This fourth intermolecular force is called ion dipole. This is a little bit weird because you only really see this when we're talking about aqueous solutions, right? So what you can do is you can kind of substitute a positive or negatively charged ion in for a polar molecule, right? So for example, if I had sodium chloride dissolved in water, water is a polar molecule, so it will have dipole-dipole force, and it will attract other water molecules through that dipole-dipole, as well as through hydrogen bonding. If I put in sodium chloride, what we're going to do is the sodium chloride will dissolve. We get positively charged sodium ions, which will be attracted to the negatively charged oxygens in the water molecule. And then we have negatively charged chlorides, which are attracted to the positively charged hydrogen end of the water molecule. Right, so you can have that type of attraction with ions as well. Right, so very similar to dipole-dipole. And the key thing here, the reason why we use this is we talk about solubility. If you can easily overcome the ion dipole force between a solvent and the water, if you can overcome the lattice energy very easily, and the ion dipole force is significantly stronger than that, then a substance will tend to be very soluble. Again, right, Coulomb's law, this is the reason why low charges, large ions, generally tend to be very soluble, because the ion dipole force between those ions and the water is stronger than the lattice energy that holds those compounds together in the ionic solid. Right, so that is ion dipole, which is kind of a fourth intermolecular force. Now let's start looking at some different properties. Right, so first property I want to talk about is viscosity. Viscosity means resistance to flow. Right, so basically like how thick a liquid is, quote unquote. Right, so water is not a very viscous liquid, but if we start pouring out like vegetable oil is much more viscous, much more thick, much more resistance to flow. Molasses is an extremely viscous liquid. It's where you get the phrases like pouring molasses in January, a very, very viscous liquid being poured at a cold temperature. Viscosity is, again, related to intermolecular forces, because the stronger the intermolecular forces are, the harder it's going to be for the molecules to move past each other and flow. Right? So strong forces mean high viscosity. Now, viscosity will decrease when you heat molecules up because they're moving faster. And molecules that move faster will basically be able to get by each other a lot easier. Right, so I gave you some examples right here. So these are different on the upper right samples of motor oil. On the right, you have what's called 10-weight motor oil. On the left, you have what's called 40-weight motor oil. Right, so the 10-weight motor oil is much less viscous, therefore it flows much more quickly. And typically you would see 5 or 10-weight motor oils, nowadays even 0-weight motor oils, used in modern cars because you need that really thin, non-viscous liquid to help lubricate the parts. Right, and also to show the relationship between dispersion force and viscosity. Again, notice the larger the molecule is from hexane up through decane, the higher the viscosity is. Right, so it goes from a very small viscosity to a much, much larger one. Our second property will be surface tension. Surface tension happens because what winds up happening is, especially with water, the fact that water is polar means that it's going to attract all the water molecules that are around it towards itself. So it'll kind of make water form spherical droplets. Right, that's the reason why when you drop water, it tends to form spheres, or when you leave it on the surface, it'll form a hemisphere. Now, at the surface, the water molecules will pull against each other, going side to side and going down, but there's nothing up, really, for them to pull against. So what that means is that the water surface will tend to form this kind of skin that very small objects can actually sit upon. So insects, for example, are very adept at being able to sit on water. You guys can also theoretically float in water if you position yourselves right, because you can make your body weight such that it's distributed in a way to not break the surface tension of the water. Right, so stronger intermolecular forces will mean stronger surface tension. Again, that's why water has a very strong surface tension. Vapor pressure. Vapor pressure is exactly what it sounds like. I went over this kind of in the last video. It is the pressure exerted by the molecules that have enough kinetic energy to break free of all their intermolecular forces and escape into the gas phase. What we have here for this graph is what's called a Boltzmann distribution. A Boltzmann distribution is a graph showing how many molecules have a given kinetic energy. What you should notice is that the higher the temperature, the higher the average kinetic energy. Molecules will have a higher energy, and it's allowed a much larger range of kinetic energy. So the graph will kind of spread out a little bit and shift to the right. What that means for us is the area under the curve after this dotted line is telling us how many molecules at each temperature have enough kinetic energy to break those intermolecular forces. Right, so the higher the temperature, the easier it is for molecules to escape, the higher the vapor pressure because more molecules have broken free. Right, so what this kind of means for us is if we look at this diagram right here, so you put ethanol into the flask, some ethanol will start to vaporize as soon as it gets into the open container. And eventually you'll reach an equilibrium where you have an equal number of molecules that escape the gas phase as you have being recaptured into the liquid phase, and you'll get a fairly constant equilibrium vapor pressure generated by this. Right, so as more molecules escape, the pressure increases. Eventually you'll hit an equilibrium where the amount of molecules that escape are equal to the number of molecules that lose enough energy to drop back into the liquid, and you'll have a fairly steady vapor pressure at that point. Vapor pressure is only dependent on the temperature of the substance, right? So for a given substance, you can actually look up charts of what the vapor pressure is at a given temperature. In fact, here is that type of diagram. So we have a graph of 4 different substances, and it's showing the vapor pressure of the liquid as a function of temperature. Right? So diethyl ether is a polar molecule, but it's not a very strongly polar molecule, nowhere near as strong as ethanol or water, which hydrogen bond. Right? So it has a very low vapor pressure, very high vapor pressure, because low intermolecular forces, it's very easy to escape the liquid phase. Ethanol, because ethanol has hydrogen bonding, it's a little bit harder for it to escape the liquid phase, so the vapor pressure is lower. Water has even stronger hydrogen bonding than ethanol does, because again, water has those 2 hydrogens attached to the oxygen compared to ethanol that only has 1. So it has an even stronger hydrogen bonding force, which means even less molecules are going to escape the gas phase or liquid phase. And ethylene glycol is basically, imagine ethyl alcohol with an OH on the other side as well. Right, so it's a really heavy molecule. Again, multiple sources for hydrogen bonding. Very, very strong hydrogen bonding in ethylene glycol, so very, very low vapor pressure. Now, one thing to keep in mind is boiling is not the same as vaporization. Vaporization is turning a liquid into a gas. Boiling is when the vapor pressure of the liquid equals the atmospheric pressure surrounding it. Right? So we have something called normal boiling point, which is the boiling point of the substance it is when the vapor pressure of the liquid is equal to 760 torr or 1 atm, right? So the normal boiling point is the temperature at which the vapor pressure is 1 atmosphere. And as we can see, diethyl ether, boiling point 34, ethyl alcohol, 78, water, our well-known 100 degrees. Now, if we talk about changes of state, the thing you have to keep in mind is that there are 3 different state changes we're going to talk about. You have fusion, which is solid to liquid at the melting point. You have vaporization, which is liquid to gas at the boiling point. And then you have sublimation, which is solid directly to gas. And if you notice, it actually gives you here a diagram of how much energy you need to get the phase transitions. It takes a lot more energy to vaporize a substance than it does to melt a substance, because again, when you melt a substance, you're only loosening the bonds a little bit, the intermolecular forces. When you're vaporizing a substance, you are completely getting rid of all intermolecular forces. So that takes a lot more energy to do. And sublimation is just the sum of the other two, right? Because you're doing both transitions at once. Now, the next graph you're going to see is a graph that you might be familiar with from sophomore year. This is a heating curve, right? Heating curve shows what happens as you add heat versus temperature. The lines A to B, the line C to D, and the line E to F, those lines are occurring because you have only one state of matter. So A to B is ice, C to D is liquid, E to F is water or steam, because we're working with water here. When you're at those points, the only thing that you're changing is the kinetic energy. So all the heat you're adding is affecting kinetic energy, causing temperature to rise, getting molecules to move faster. Once you get to the line B to C and the line D to E, you'll notice the temperature remains the same. The reason why is because at those points, at the melting point and at the boiling point, all of the energy that you're adding is going to weaken and then completely remove the intermolecular forces that are present, right? So the melting line, you're separating the molecules enough so that the liquid can flow. It's a potential energy change. D to E, you're completely getting rid of the intermolecular forces as you separate out all of the molecules entirely. Again, potential energy change. So wherever you have the horizontal line, that's potential energy, intermolecular forces. The vertical lines are kinetic energy. And when we do thermo, we'll go through how to calculate all these, right? So the A to B, so the like single phase lines, the more vertical lines, you can figure out heat changes using your MC delta T. The other lines you can figure out using what's called heat of fusion or heat of vaporization times some quantity, either mass or moles. Right, so these are different properties of condensed phases, liquids, and solids, and how intermolecular forces kind of affect those. In the next video, we're going to talk about solids and some other special types of materials, and I will see you guys then.